Okay, now we have 6.4 additional properties of linear transformations. Let's take a look at the two transformations together and we'll see what we could do. Additional properties. Definition. If T1 goes from U to V vector spaces and T2 takes you from V to W. You could see that V is highlighted now. It's almost like you're going from U to V and the same V, you're continuing to W through two steps. So T2 is my second step. P, two linear transformations. We define the composition or product as T2 T1. We read it as also T2 of T1 or after T1. This is gonna start from U right here. It's gonna end up with W right here, all the way. As you can see, V is not mentioned. By T2 T1U as T2 of T1U for all U in the vector space U. Now let's look at an image that describes what's going on. Notice that T1 takes you from U to V, T2 takes you from V to W. So if you want to go all the way from U to W, it's called T2 after T1. As a picture, here's the vector space U with small vectors inside as small u. Through T1, they're gonna go to TU or T1U. If you take this as an input and you apply the second transformation T2, we get T2 of T1 of U, which is a product T2 T1U. Notice right here, you could call it like a shortcut. We're going directly from U to W, and it's called T2 T1. Let's look at a theorem right here. If T1 is a linear transformation, just the way it was stated, and T2 is also a linear transformation, then the product T2 T1 from U to W is also a linear transformation. Here's an example. If T1 goes from R to the N to R to the M with a matrix of transformation A with a size of M by N, T1 of X will be written as AX, where X is a vector in R to the N. T2 takes you from R to the M, same right here, to R to the P, defined as T2 of X equals Bx. B is a matrix of size P by M. Pay attention to the sizes right here, P by M, P by M. The matrix A size is M by N, M by N. Just keep in mind that it's kind of like written backwards. That should help in solving some problems, and we mentioned that in previous section. Now, we want to determine the composition or the product of those two transformations, T1 and T2. To determine T2 T1, that takes you from R to the N all the way to R to the P, we define it as follows. So we'll start step by step. Let's take a look. T2 T1 of X will be T2 of T1 of X. We want to replace T1 of X with what is given to me or defined as AX. Let's do that. So instead of T1 of X, we wrote A of X. But how T2 works, you just multiply any input by B. the matrix P. Here we go. So we multiply B times AX, which means I could write it as BAX. That is, T2, T1 of X equals B times A times X. B times A is a matrix of a new size, which is B, P times N. P times N. P times N. Because you're going from Rn to Rp, so it's P times N. This is what I just mentioned. If you see it as a product B times A, M matches, and the size, the new size will be P times N. Let's look at an example. This way, or in this example, T1 of A matrix of transformation becomes A plus A transpose. And we're going from MNR to MNR. Matrices of size m by n with real numbers or elements inside. T2 takes you from MNR to the set of real numbers by taking the trace of A, which is the sum of the elements in the main diagonal. So we're going to apply and see or define what's T2, T1. T2, T1 is mainly what we're trying to write step by step. So let's start. T2, T1 of A, we could say T1 of A first, and T1 of A is A plus A transpose. So we replace T1 of A with its definition. As you could see, it's A plus AT or transpose for T1. Now what T2 does, takes the trace of that. So we need to say trace of the sum of A plus A transpose. Okay. Now what's the trace of A plus A transpose? If you didn't know, here we go. It's twice the trace of A. So my answer is, what they want us to write or determine T2, T1, it's actually twice trace of A. Let's see why, or just like a note as an example. As an example, if A equals 2, -1, -3, 6, then the transpose will read as 2, -1 instead of the first row. You read it as the first column. -3, 6 will be the second column, -3, 6. Notice that the main diagonal is the same, 2, 6, 2, 6. Trace of A is 8. Trace of A transpose is also 8, 2 plus 6. How about if you add the two matrices? 2 plus 2 is 4. -1 plus -3 is -4. -3 plus -1 is -4. 6 plus 6 is 12. The main diagonal adds up to 4 plus 12, which is 16. And notice that 16 is twice 8. So trace A plus A transpose is twice trace of A. Definition. If T takes you from V to W is a linear transformation, we have the following. We call the transformation T one-to-one whenever you have two different inputs. V1 is different than V2. We end up with different outputs. TV1 will be different than TV2. Onto every W as a vector in the vector space W is an image to some element or input in V. The main part is the first one. You have to pay attention to the way it's written. You could see it in another way as follows. Notice that number 1 is equivalent to the following. If these two are equivalent, going back, that will give you these equivalent. Okay? That's the definition of one-to-one, which is the other way around of defining functions, if you remember. Let's look at an example. This example says we're going from matrices of 2 by 2 with real numbers to set of real numbers. So we're going from matrices to numbers. How? By applying the trace. Applying the trace of A, which is sum of the elements in the main diagonal. Now in this case, T is not going to be one-to-one, and let me show you why. Look at this picture. If you pick as an example an element 0 in the set of real numbers right here in W, this could be coming from 0, 1, 0, 0. The trace is still 0. 0, 2, 0, 0 will also give you a trace of 0. Two different elements give you the same output. That is not a one-to-one. Notice that the images are the same, but A does not equal to B. This is what I mentioned earlier right here. The images are the same. We should end up with the inputs being the same. So I'm using this right here. Next, T is going to be onto. Why? To explain it, if you take any element, any number in R, which is W, this will be an image to some vectors right here, which is a matrix of 2 by 2. Could be more than one. That's what does not make it a one-to-one function. Since every real number, W in R, is an image of some matrix in M2R. For example, take A equals W 0, 0, 0. Notice that W is a number and it belongs to the set of real numbers. Then TA equals W. TA is the trace of A. W plus 0 is just W. Theorem. The transformation T that takes you from V to W would be one-to-one if and only if kernel of T equals 0. Onto if and only if the range of T covers the whole vector space W. This is something that you should remember. It's kind of common sense. Onto means it covers the whole thing. So the range is covering the whole W that we're going to. The first one is critical. You need to use it once in a while, especially when you solve problems. One-to-one if and only if the kernel is only 0. Imagine in the first slide or second slide when we graphed the picture of the kernel, it's a set of vectors that gets mapped to the 0. Well, in this case, 0 only takes you to 0. Nothing else takes you to 0. So the set of solutions to Ax equals 0 is just the 0 vector in V. Example. Let's show that the following transformation is onto. We're going from R to the 7 to R to the 5, being given to me as a linear transformation. And also I'm given that the dimension of the kernel of T equals 2. Show that T is onto. Basically, we need to figure out the dimension of the range. Because I don't have the rule right here. It doesn't say like how do you go from R to the 7 to R to the 5. I'm just giving some numbers like dimensions. Let's see what we could do. Since T in general goes from V to W, so our V in this case is R to the 7. And the dimension of V, which is R to the 7, is 7. keep this in mind. We have the dimension of V, that's V. We have the dimension of the kernel, and now we're going to use the theorem that we mentioned in the last section. I have the dimension of the kernel equals 2, given. I have the dimension of V equals 7, because V is R to the 7. That should add up to what? This is a 2, this is 7, that has to be 5. The range has the size or dimension of 5. But what is W? W is also with a dimension of 5, which makes sense and it adds up. Since W equals R to the 5 and the dimension of R to the 5 is 5, we have the dimension of the range is exactly the same as the dimension of W. They're both 5, so onto as expected. Here's another example. We're going from R to the 3rd to R to the 6th. And one more time, we're not giving the rule, we are giving some numbers. Dimension of the range is 3 now. Show that T is 1 to 1. Sorry. Here we go. The dimension of the range is given to me as 3. The dimension of V is R to the 3rd. So that should be 3. Well, in this case, we're adding 3 to what? To end up 3. So the dimension of the kernel has to be 0. But when the dimension of a set or a subspace is 0, it should have only the 0 vector by definition. So the kernel is only the 0 vector. But if you remember back to this right here, I'll show you. This right here. If the kernel of T equals 0, that means, according to this theorem, it's 1 to 1. Let's go back. So because of the kernel of T equals 0, we end up with T equals 1 to 1, and that's it, as expected. Here's another example. Show that T is onto. We're going from P6 to R to the 5. This is V, and the size of V is the size of P6, which is 6 plus 1, and that's 7. Remember, the size of polynomials of degree n is n plus 1. W is R to the 5. The size of W is 5. And we could see it from here. We need this for the range and onto. Dimension of kernel of T is 2 is given to me. Let's use the theorem and we'll compare the numbers together. So what I just mentioned in writing, it's right here. We're going from V to W. Today it's P6 to R to the 5. The dimension of V is 7. Dimension of W is 5. 7, 5. Here's the theorem. The theorem says the dimension of the kernel plus the dimension of the range should add up to the dimension of V. V is 7. Kernel is 2, given. 2 plus what equals 7? That should be 5. If this is 5, but the W has a size of 5, as you could see up here, so the dimension of the range is 5, which is the same thing as the dimension of W. That means onto. Okay, next. This is a lengthy example, so let's take it step by step. We're going from P2 to P2. This time we're giving the rule. Kind of lengthy, but that's what we have. We're gonna have to deal with it. Determine whether T is 1 to 1, onto both, or neither. A polynomial of second degree as an input in general looks like a plus bx plus cx squared. to go to the outputs is still in polynomials of second degree, as you could see. Let me start going backwards, it's easier to read it. To get the coefficient of x to the second, it's a cx to the second, same as this. To get the coefficient of x, it's b minus 2a, b minus twice a. To get the constant, it's twice a minus b plus c. You just follow the rule. So let's take it step by step. We're going to discuss now one-to-one in detail, then we'll move on to onto. One-to-one. One way to see it is if the kernel of t is 0. If the kernel of t is 0, we're done. It's one-to-one. If the kernel of t is not 0, it's not one-to-one, according to the theorem that was mentioned a while ago. But to define the kernel, looking at this, I'm going to slow down and let you follow me step by step. We're going to have to define the kernel and see the basis of the kernel. If the only vector in kernel is 0, we're done, one-to-one. If it has more than 0, or if it has bases, if it has vectors that you could span, it's not going to be one-to-one. So, according to the definition of the kernel, it's vectors in P2 right here, such that the outputs takes you to 0. That's how the kernel is defined. But how can I rewrite this again? TP equals 0. What's TP? That's TP. This whole thing should be my output. But for now, they want the output to be 0. So let me write it down right here. We have the input, and we want the output to be 0. This is my output. This is my output. I want my output to be 0. This is my inputs. All the vectors of this format that belongs to B2, such that when you end up applying the transformation, you get this much. Focused to be 0, we are dealing with the kernel. But if that is 0, that means every single term is 0, which means everything is 0 as coefficients. Here we go. C equals 0. B minus 2a equals 0. 2a minus b plus c is also 0. Just with simple algebra steps, we end up with c equals 0 as is. From the second and third one, we end up b being twice a. So, as far as I could tell, it's not one-to-one. But let's move on further. If another question asks you to write the basis for the kernel and, what does it span, dimension, we need to move on. Here we go. As you know, usually examples are meant mainly for discussion and covering ideas. So the kernel is a set of vectors in P2 with this condition. C should be 0, so this is gonna be gone. And B is equal to 2a, twice a. So we're gonna simplify this according to these two conditions. A plus 2a, x plus 0x squared. Instead of b, I wrote 2a. Instead of c, I wrote 0. One more time. Simplify more. Okay, it's a plus 2ax. I don't need this term. Factor a out. Now what do I see? 1 plus 2x. So the basis for the kernel is the vector 1 plus 2x. The kernel of T contains non-zero vectors. The kernel of T is not equal to the 0 set. Therefore, it's not one-to-one. That's using that theorem. Let's move on to onto. To work on onto, I'm going to use the theorem that talks about the dimensions. because I have P2 right here, and I could find out the size of W. I have now the dimension of the kernel. What do you think the dimension of the kernel is? If it has only the 0 vector, I was expecting that, we will call it a size of 0. But it has a basis as 1 plus 2x. So instead of wasting your time, let's see the steps in writing. Here we go. We have the dimension of the kernel of T plus the dimension of range of T equals the dimension of V. I keep repeating that and I keep using it. Hopefully now it's known for all of us. The kernel of T is a span of the vector 1 plus 2x. Only the form of 1 plus 2x gets mapped to the 0. So what's the dimension? It's just one vector, 1. Also the dimension of V, which is P2, is 2 plus 1, which is 3. I'm going to go back right here and compare my numbers. Dimension of range is 2. Think of this as 1. Think of this as 3. This has to be 2. It has to add up to 2. Dimension of W, that says W, is 3. Dimension of range is 2. That's not going to add up. Dimension of range is 2, because we said 1 plus what equals 3. That should be 2. The range should be 2. But W is 3. So if W is 3 and the range is 2, they're not equal, which means not onto. Okay? As you can see, it's a little bit lengthy, but it's worth slowing down step by step. Especially, it's not just like comparing numbers using the theorem directly. It's looking at a transformation that is given to me. Here's some things that you want to keep in mind. Theorems and parts of theorems or propositions. If T takes you from V to W as a linear transformation, and V and W are both finite dimensional, then number 1, T is 1 to 1 implies that the dimension of V will be less than or equal to the dimension of W. Number 2, T is onto implies that dimension of V is greater than or equal to the dimension of W. Well, what about both? T is 1 to 1 and onto. That means the dimensions are equal. The third one is common sense. If you remember in functions, 1 to 1 and onto, that means everything gets mapped. It has an inverse going backwards. So it's the same size. Could be going from ABC, 3 letters, to another 3 letters, 1 to 1, back and forth. So this is obvious. Onto, that means V is bigger overall. Everything has to have an image. So you're going to cover W. That's onto. Anyway, here's another one. V and W are finite dimensional vector spaces. Given also that the dimension of V is the same as the dimension of W. Then, T is 1 to 1 if and only if T is onto. This is like part 3 going backwards. So when you go backwards, if you have dimension of V equals dimension of W, and you prove in your steps that it's 1 to 1, you're done. It's going to be onto. Or, given this, and you prove that it's onto, done. Because that is if and only if. Here's the theorem. If T takes you from R to the N to R to the N, same size, a linear transformation with matrix A, then Number 1. T inverse exists if and only if the determinant of A does not equal to 0. Notice what we're looking at, matrix transformation. Next, number 2. T inverse will take you back from R to the n to the R to the n is a linear transformation with matrix A inverse. Here's something that in this section you want to keep in mind, which is not too complicated, but it's a new name or phrase that we use. Isomorphism. T takes you from V to W. If there exists a linear transformation T from V to W that is both one-to-one and onto, we call T an isomorphism. We say that V and W are isomorphic vector spaces. In short, we write it this way. Pretty much like V and W are equivalent. Same size. Everything is nicely connected from V to W, back and forth. Let's take an example. This is a simple example, but I'll take my time as steps to show you step by step what's going on. If they say you have two sets that they are isomorphic or determine isomorphism between them, we have R to the 4 and M2. Before I start, notice that R to the 4 is vectors of the form A, B, C, D. So it has 4 elements inside or 4 spots inside. At least that's one way to look at it. M2 is a size of 2 by 2, and usually we read the numbers as A11, A12, A21, A22, but let's call them A, B, C, D, just to see how can I connect back and forth between R to the 4 and M2 and make it one-to-one and onto. Next, so we're going from R to the 4 to M2. We need to define some kind of transformation. If you have something here that's called ABCD, how can I see an image right here? So let ABCD be a vector in R to the 4. Then A as a matrix ABCD in M2R could be connected to this or rewritten this way. A times 1, 0, 0, 1, B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1. So you could see it even backwards. If you have a matrix right here, you could write it as a linear combination, and you pull out ABCD and write it as ABCD. So you could see it both forward and backward. We can define an isomorphism T that takes you from R to the 4 to M2 by the following, and that should do it. Here we go. That's it. As simple as that. I had to wait and show you step by step so you could think with me what's going on. It's so simple that there is no need to spend that much time on it, which is one-to-one and onto. So if you have 5, 6, 7, 8, that should be coming from 5, 6, 7, 8. That's it. And forward too. So that's it. Thank you for watching. If you like this video, you know what to do. Until next time, peace. Jabber time. That's it.